Thank you, Scott. My name is Tony Gibbs, and I'm a data warehousing solution architect here at AWS.
My name is Himanshu Raja. I'm a senior product manager with Amazon Redshift.
And today we're going to be going over best practices on scaling Amazon Redshift. So just going into the overview of what we're going to be covering today, we're going to start out with the history and development of Redshift. This is really just kind of a high-level just overview of Redshift and how we started it, how we do development. And this is kind of meant more for those of you who haven't really used Redshift before and aren't familiar with it. After that, we're going to jump into some architectural concepts and just kind of go through some of the terminology and such so that when we're talking about scaling Redshift, you're familiar with those concepts. Then we're going to jump into the scaling piece, and this is where Himanshu is going to introduce to you the new Elastic Resize. And then I'm going to wrap up with best practices using the copy statement and how the new Elastic Resize can potentially impact the copy statement. Once we're done, we'll do a short Q&A with whatever time is left over. So we'll just get started here with the history and development of Redshift. Redshift starts out from Postgres. Originally, it was forked off of Postgres, and what we ended up doing was making it Columnar. So Postgres is a row-based database. Redshift is a Columnar data warehouse. We also made it MPP. That's massively parallel processing, and that's so that we can scale out Redshift up to 128 nodes and 2 petabytes of raw storage. We also then added a lot of OLAP functionality, think windowing functions, approximate functions, and that sort of thing. We wrapped all of this up in the AWS ecosystem. So this is integration with S3, our IAM for authentication, KMS for full data encryption. And it really is kind of the combination of all of these things that make Redshift what it is. We launched Redshift almost 6 years ago. It launched on Valentine's Day, February 2013. And since that time, we've been innovating at a rapid pace. We've been releasing patches typically every 2 weeks. And since that time, we've released over 180 significant features and services to date. And we'll be talking about one of those features in depth in this webinar. So going into the architecture and concepts. As I mentioned before, Redshift is an MPP data warehouse. How it works is you connect to what we call a leader node using your SQL and BI tools. We supply ODBC and JDBC drivers for the connectivity. However, because Redshift was forked off of Postgres, it actually still supports the open source Postgres drivers. So for example, if you were connecting with Python, for example, you can use the open source Postgres drivers to connect to Amazon Redshift. Behind the leader node are 2 or more compute nodes. Those compute nodes are where the data actually resides. So when you're querying Redshift, what would end up happening is that data would be spread evenly across those compute nodes, and every one of those nodes would participate in executing the query entirely in parallel. That's how Redshift is able to scale to such high performance. Then beneath Redshift, we have Amazon S3. So this is the integration with S3 that I was mentioning before. You can load data directly into Redshift or unload it if you want to remove data out of Redshift. Or you also have the option to query Redshift with what we call Amazon Redshift Spectrum, which is an elastic layer of compute that sits between your compute nodes and S3. So the first piece of terminology, just to kind of introduce you to, for those of you who aren't familiar with Redshift, is Columnar. So Redshift is what we call a Columnar Architecture, and that means that we store the data on disk column by column rather than row by row. The goal here is to reduce I/O for the types of queries that you typically do in an analytics data warehouse. Just to illustrate how this works, suppose we had this very simple table. It's just a table with 3 columns and a handful of rows in it. If we were to select and run this select query, this select a minimum date from this table, in a row-based database, you'd end up scanning the entire table. However, in a columnar data warehouse, because we're only accessing a single column, we only need to read that single date-time column off disk, thus reducing I/O. The next important concept to introduce you to is what we call slices. Slices, you can kind of think of them like virtual compute nodes. It's how we get the parallelism within each one of our compute nodes. So for example, in that previous example where we had 3 compute nodes, those nodes would be comprised of either 2 or 16 slices, depending on the size of the instance. Each one of those slices is really what runs everything in parallel, and the data is distributed per slice. So talking about moving into the compute nodes, what we have is we have 2 different flavors of these. We have our dense compute and our dense storage nodes. And the main difference between them is the fact that the dense compute are made up of SSDs, whereas the dense storage are made up of magnetic disks. Then we have a smaller version and a larger version of each of those. And that's why there's a difference in slices. If you look on the far right of the table, you'll see that, for example, the DC2 large is comprised of 2 slices, and the DC2 8X large is comprised of 16 slices. So that's so that we can get parallelism as the node size increases. So I'm going to move into how we typically scale Amazon Redshift today. Now we have a few different options here. The easiest is you can resize. It is very easy to use. You simply go into the console, you click resize, type in the new number of nodes that you want, and the data is transferred from your old cluster to your new cluster, and your cluster will then be at the new size. The other option is Amazon Redshift Spectrum, which I spoke about earlier when we were going over the architecture. What this does is it allows Redshift to query S3 directly with that elastic scalable compute layer. And that offloads work out of your Redshift cluster and allows you to scale further. Another option that some customers also do is they will create a snapshot of their cluster and spin up a parallel query and say, maybe use that other snapshot or that other query or cluster for maybe doing end of month reporting, end of quarter reporting, and then throw the cluster away when they're done. So those are just some of the techniques that are used today. Now I'm going to go into how the resize currently works. So we're going to be calling this classic resize going forward. And what we essentially do is we, in the background, spin up an entirely new cluster. So for example, with what you're looking at the screen, I'm going from a 3-node cluster to a 6-node cluster. We spin up this whole new cluster. We drop your primary cluster into read-only mode, and we binary stream all of the data over from the old cluster into the new cluster. One really nice benefit of this technique of how we're doing resize is that you can move from, say, magnetic disks to solid state, or from solid state instances to magnetic disks. So there's a lot of flexibility with the way that we've implemented this. Now I'm going to hand the presentation here over to Himanshu, and he's going to introduce to you the new Elastic Resize and how it works.
Thanks a lot, Tony. So I'm excited to announce Elastic Resize today. With Elastic Resize, now you can add or remove nodes in minutes. The typical user experience with Elastic Resize is that the cluster is unavailable for few minutes, during which we hold most of the read and write queries, and after the resize is finished, read and write queries start executing. What Elastic Resize allows you to do is to scale storage and compute quickly on demand, which basically enables you to speed up read and write query performance. You can also run ETL jobs faster, finish copy, and unload quickly. Because Elastic Resize is so fast, you can do this on monthly, weekly, or daily basis in order to save cost and get the extra storage and compute when required. In the next slide, I will talk about why Elastic Resize is so fast. So here you are looking at a Redshift cluster. The original size of the cluster was 3-node Redshift cluster. And then with Elastic Resize, we added 3 more nodes. So Tony earlier introduced a concept of slices. So initially, let's assume this is a DC2 8XL cluster, 3-node cluster, and it had 48 slices. With Elastic Resize, if you were to double the size of the cluster, what we will do is we will add 3 more nodes and just move the half the number of slices to the new nodes. So what is happening here is that we are adding or removing nodes in the same cluster, which means that the less data is to be moved and the fewer net operations are to be done versus the classic resize where we were bringing up a brand new cluster and moving data from old cluster to new cluster. So here in Elastic Resize, the leader node remains the same, the endpoint remains the same. So now let me talk about how you can use Elastic Resize. You can do Elastic Resize via 2 ways, using the AWS Management Console or using the CLIs. With the console, it's really easy. You can choose between Elastic Resize or Classic Resize. By default, if you have an option of doing Elastic Resize, you will get that as a default option, and you can choose any number of nodes that are shown on the console. If you were to change the node types, you would need to do a Classic Resize, and then you can select that on the console. For the CLIs as well, you can use the resize cluster command, and the resize cluster by default also does Elastic Resize. Now let me talk about how Elastic Resize works and what the user experience is. So when you click on Elastic Resize, the very first thing we do is to take a snapshot and make a most recent copy of the data in S3. As you know, in Redshift, automated snapshot is taken every 8 hours or 5 GB of data change. So what we are doing is we are taking an incremental snapshot to back up the data from the last snapshot that was taken. Once the snapshot is taken, that's when we start the next stage. During this stage, the cluster is available fully available for read and write. And the time duration can be anywhere from 15 minutes plus minus 10 minutes. The time it takes to complete this stage depends on when the last snapshot was taken. If you want to minimize this time period, you can take a snapshot before starting an Elastic Resize. Once a snapshot is taken, during this, the next phase kicks off, and that's when the Elastic Resize actually happens. During this time, the cluster is unavailable for all read and write queries. We hold all the connections, and we hold most of the read and write queries. Some of the queries may get killed, especially if the queries were already that started getting executed when the resize kicks off. Those queries will be killed. So during this time period, we are adding new nodes or we are removing nodes depending on if you are doing scaling up or scaling down. And that is during this time period, we are shuffling the slices. Once this phase is complete, the cluster comes back up online and is available for read and writes. During this time period, now what we are doing is we are transferring data back to the new nodes that were added, or in case you remove nodes, the data is then consolidated into the remaining nodes. The cluster is fully available for read and writes, and in order to make sure that during this phase, there is minimal impact to the user queries that were coming in, we did a couple of performance enhancements. So the first thing that we did is we prioritized the data block based on the hotness of the data. So we are moving the data blocks which are frequently accessed first, and then in that order, we are moving the other data blocks. And then the other improvement that we did is we speeded up the rate at which we hydrate from Amazon S3 back to the Redshift nodes. So once the Elastic Resize is finished, the cluster continues to be available for read and write queries, and you have the new state of the cluster available. So now let me talk about when to use Elastic Resize versus Classic Resize. When you want to scale up and down for workload spikes, we recommend to use Elastic Resize. the fact that Elastic Resize is really fast compared to classic Resize makes a perfect use case for scaling up and down on demand. When you want to add incrementally storage or remove storage, then also Elastic Resize is the perfect choice. However, if you want to change the instance types, say you want to move from an SSD-based instance to HDD-based instance, an example could be when your data sizes are increasing and you want to move from DC2.8x large to DS2.8x large. In that case, you would want to use classic resize. Or if Elastic Resize is not an option available, then you also use classic resize. Here, an example could be that if you have a 10-node DC2.large cluster and you only want to add 1 or 2 nodes rather than doubling the size of the cluster, you would want to use classic resize. The biggest difference between Elastic Resize and classic resize is the unavailability time, the limited availability time during resize. In Elastic Resize, the cluster is unavailable for only 5 to 10 minutes, where most of the connections are parked, versus the classic resize that can take anywhere from 1 to 24 hours, where cluster is only available in read-only mode. Now, I'm going to hand to Tony to talk about the best practices for copying.
Thank you, Himanshu. All right, we're going to talk about the copy statement and how it's optimized based on the number of slices in the cluster. So up on my screen right here, I have an example with a single DC2 8XL compute node. In Amazon Redshift, if I were to issue a copy statement and load this single file, what would happen is the leader node would check S3 and say, there's one file on S3, and it would ask the first slice in the cluster to load that file, to parse it, to distribute it, and get it all written to disk. In this particular example, this wouldn't be very efficient. We're only using 1/16 of the cluster. If, on the other hand, I took that same file and I broke it up into 16 smaller files, what would happen is the leader node would see all 16 files on S3 and have the compute node load all 16 of those files entirely in parallel. This operation, or doing it like this, actually scales perfectly linear. So this would run roughly 16 times faster than the previous example. Our recommendation for loading data with the copy statement is to use delimited files, and these files ideally should be somewhere between 1 meg and 1 gig after gzip compression. So just to kind of summarize the best practices for copy is basically, like I said, use delimited files. I usually recommend picking a simple delimiter like a pipe or a comma or tab, something like that. Picking a simple null character, usually \N works well. And make sure that you have double quotes around your varchars and use an escape character like / within the varchars. Now, the part that I said has changed is the number of slices in the cluster. When you use Elastic Resize, the total number of slices no longer changes. So say, for example, if you started out with a 4-node DC2 8XL cluster and you incrementally resized, say, up to 6 nodes, the total number of slices in the cluster wouldn't change. So previously, you would probably just look at the documentation and say, okay, there's 16 slices in each node. I have 6 nodes, multiply the 2 together, and that gives you the total number of files. Because that no longer is the case, what you'll want to do is you'll probably want to check the number of slices in one of our system tables called stv_slices. If you just count the number of slices in there, that'll give you the global number of slices in your Redshift cluster. Our best practices for the number of files is that there should be an equal number of files as you have slices or a multiple of that. So for example, if your cluster had 64 slices, 64 files would work really well, as would 128 files, just as an example. And we've also added in here a handful of links and such just for the documentation here on Elastic Resize, Classic Resize, and where you can find the CLI and API calls that Himanshu was talking about earlier. So this is all of the documentation in relation to our resizing. Thank you very much for tuning in to today's webinar. We'll take questions from here.